So in this lecture we are going to talk about the Laplace transformation. It is also an integral transformation. Oops, sorry. So just like Fourier transformation, the Laplace transformation is also integral transformation, and it can be regarded as a more general version of the Fourier transformation itself. So this is a more general transformation. Now the question that arises, why is it called a more general transformation? So if we recall that the Fourier transformation for a function, let's say a function of x, if we wanted to Fourier transform it, then this would be just an integral from minus infinity to plus infinity. Then we would have our f of x, then we would have e to the power I px, and finally we would have a dx, right? And there is some numerical factor that we chose. You can also choose 2 pi, but that is not really relevant here. As you can see that the very idea of whether a Fourier transformation of some function f of x exists or not will totally depend whether this integral converges or not. So the existence of some Fourier transformation of some function f is dependent on the existence and obviously the convergence of the integral. Now, using Jordan's lemma, you can easily show that if as x goes to infinity, as in this limits, because this is improper integral, as x goes to infinity, if this function itself doesn't converge, then this integral won't converge. So in short, what we can say is that as x goes to infinity, if the more general notion is the modulus of this function, if this thing doesn't go to 0, then the integral, or so to say the Fourier integral, does not converge. And that's the problem. This is a problem, because if the integral doesn't converge, then the integral blows up and we get infinity basically. So that doesn't mean anything physical. So that's why we shift towards this Laplace transformations. This is one of the many reasons that we want to do this Laplace transformation. And an example where the integral, the Fourier integral, doesn't converge would be to consider. So this is an example, is that consider some function f of x equals to x, just x. If you think of x to the power n like this, you can also think of that where n is some integer. Then you can obviously see that this integral doesn't converge. And how do you see that? Just using Jordan's lemma. Alright, so that's why we want to go towards the Laplace transformation. So now let's try to define Laplace transformation. So this is the definition of Laplace transformation. So let's say you have some function f of x, and you can start from 0 to infinity. This is how it is defined, and just like Fourier transformation, but this time you gave a e to the power minus. Let's say the dual basis is now s, and you have x like this. Or you can also choose other dual bases as well, for example p, just like we did for Fourier transformation. So this is how you can write it, and you are integrating over x, and what you have is the Laplace transformation version. I can use the tilde to denote that this is actually a Laplace transformed version of the function f of x, and this is coming in terms of s, right? This is the definition of a Laplace transformation, and we can try to see an example. For example, let's say let our f of x be x cube. Alright, so let's try to take that, and so f tilde of s would be just this integral, x cube e to the power minus px dx, right? How do you evaluate it? Pretty simple. You just integrate it by parts, and then you are good to go. So if I write down a few lines, is that first what you want to do is that you want to integrate this e to the power minus px with respect to x, and what you have is minus 1 upon p e to the power minus px x cube from infinity to 0. And what you can see over here is that as x goes to infinity, the function itself doesn't converge, but what happens over here is that in Laplace transformation you have this exponential decay factor, so that's why it forces you to converge as x blows up or x goes to infinity. Alright, and when x is 0, this is just 0, right? So this term eventually goes away, and now what you have integration by parts. That's what we're doing. You have a minus sign, you go from 0 to infinity, you put 1 upon p e to the power minus px like this, but now you differentiate this x cube, right? So there should be a 3 times x square, just like that. And now again you can integrate it by parts, and you can derive the final result, which I'm not going to write here. This will be something that will come in terms of p, not s. It should come in terms of p, since I'm considering p as the dual basis to x. Or you can also use the gamma function thing that you see. If you can write it like that, you can easily evaluate it in one line. It's as simple as that. Now, just like Fourier transformation, Laplace transformations can also be used to find solutions of partial differential equations. That's the main use of it. But for now, to keep things simple, we will only consider ordinary differential equations. So we are calling it application to ODE, or ordinary differential equation. So again, a differential equation can be written as, let's say, second order. We won't go into the higher order thing, but the analysis would be similar. Let's say this is g of x. I'm assuming a, b, c, all of them belongs to the real number for simplicity. Now what we have to do is that we actually have to find an algebraic equation, because that's what we did when we tried to do the Fourier analysis, right? So we have to turn this differential equation into an algebraic equation. Let's try to do that with the Laplace transformation. So for that we have to Laplace transformation both sides, and I'm denoting with the calligraphic L. Now since this is a number, it won't have an effect, because this is just a number and it goes outside the integral thing, right? And then you have this y double prime, that means d square y dx square. But you can apply this integral that is defined as the definition of the Laplace transformation over this operator. So Let's try to do the most simple thing first, the y prime, that is the first derivative of y. We want to find its Laplace transformation. And why we are not bothering with y? Because the Laplace transformation of y would be just, y of x would be just y of, let's say, p, like this. So that's why we are not bothering with this. Our goal is to find some y of p, and in next lectures you will see how to do the inverse Laplace transformations. And once you find this y of p, you do an inverse Laplace transformation using a Bromwich integral to get the solution. So now we try to find what is, this is the thing we want to find. So how do we do it? Just use the definition of the integral, that is 0 to infinity, then we have this dy dx, we have e to the power minus sp, let's say, and we are integrating over x. This is what we have. So it's pretty straightforward to integrate. You have y of x e to the power minus sp at 0 to infinity minus y of x e to the power minus sp oops, sorry, it shouldn't be sp, it should be xp, not s. Sorry about that. And then you have this e to the power minus xp, and you have this d of x, right? And as you can see, when x goes to infinity, because of this negative exponential factor, it will go down and it will go to 0 regardless of what y of x is at infinity. Alright, and then when you have this 0, you will only have minus y of 0, right? Okay, so this type of thing appear in a differential equation as a boundary condition most of the time. If you are considering an interval from 0 to infinity, let's say, then 0 would be a boundary point. And this is what, this part is nothing but the Laplace transformation of y. However, if you note carefully or notice it, that we are missing something from here, because we are integrating by parts, so we have to differentiate this e to the power minus xp with respect to x. And what we will get from there is that we'll have one minus sign coming downstairs and a p, right? So there should be a p and there will be another minus sign, and these two minus signs will cancel each other and result in a plus. So this is just y of p times p. This is the result. Let's call this result as number 1. And then we want to find the Laplace transformation version of the second derivative, right? This is a similar analysis like before. So you just write all these things down. P of x dx, you integrate by parts. What you have on the left hand side would be something like this, e to the power minus px, and you have infinity to 0, and this will just give you a y prime, that means the first derivative evaluated at the point 0, and there will be a minus sign, and then there is another minus sign, and this will give you 0 to infinity. What you have right now is dy dx e to the power minus xp dx, and again you need to take the derivative of this exponential since you integrated the second derivative of y in the first part. So if we do that, we have a plus and we have a p. So if you take this p out, you see that this is nothing but the Laplace transformation of the first derivative, which is just the result 1. So this is coming as p times minus y0 plus y of p times p. So if you multiply this thing with p, you will have a y prime of 0 minus p y of 0, and then you'll have a plus p square y of p, and this is the result for the second derivative. Now all you gotta do is that, let's say this is the result number 2. Now all you need to do, put 1 and 2 into the differential equation that we were considering, that is this guy. So if you do that, what you have right now is that capital A times minus y prime 0 minus p y 0 plus p square y of p. Obviously you can neglect this possible symbols or possible variables, but in that case make sure you know what you're doing. For clarity I'm just keeping them. Then you have this b, and the first derivative result was minus y0 plus y of p times p, and finally you have c y of p, and we are assuming the Laplace transformation version for our arbitrary function g of x will be something called a g of p, right? So this will be g of p. Now what you have is an algebraic equation in terms of y of p. So from here you can solve for y of p. So let me write that down. So from here you can solve for y of p and then use the inverse Laplace transformations to generate a solution. Now how the solution will be, it will totally depend on whether these values, these boundary values, whether they're given or not. If they're not given, then you get some general solution. If you are given those boundary conditions, then you will have a particular solution. It is as simple as that. So this is how we do this Laplace transformations, and in the next lecture you're going to learn about the inverse Laplace transformations, which will totally depend on contour integrals and the residue calculus. So in this lecture you haven't seen anything complex, but in general these values can be complex as well. But it's the inverse Laplace transformation that actually makes you appreciate the power of the residue calculus. So this will be it for today, and thank you.